All right. Finally, chapter 7. It's bittersweet, right? It's our last chapter, but it's also, I think, the most fun chapter. I save it for last because it kind of ends us on a high note, which is always nice. And it's going to build on basically building straight lines, which is maybe familiar from other math courses you've taken at some point. And so we're kind of back to, okay, we can, there's no hypothesis testing, although we could. We're not going to, but I'll show you how you could, but we're not going to in this course. So we'll just focus on building a line of best fit. So regression sounds weird, but it's really just fitting a line of best fit. A line of best fit, which I remember, I'm pretty sure it was chemistry, like chemistry, maybe 11 or 12. But anyways, we had this data and we had plotted it on our page, I guess. Why weren't we using software? I'm not like that old, but I guess, yeah, anyways, it's neither here nor there. But I remember the teacher saying, okay, now draw your line of best fit. And we all got our rulers out and you just kind of drew your line of best fit. It's a little bit more complicated than that. We're not going to do that. We shouldn't do that. But it's not that bad. So anyways, so regression is basically a fancy term for fitting a line of best fit. And we use it to model a relationship between two variables. So we are going to focus on two numerical variables, right? There, I did it. I highlighted it. So I want to focus on the relationship between two numerical variables because that's the most common thing that we deal with. And then if you've seen that, you can kind of build on that in other courses for other combinations. But before we can fit some lines of best fit, we have to talk about some theory, of course, and a lot of that is going to be around the correlation. Now, you've probably heard the word correlation, or at least correlates, and we understand from just kind of life that when we say correlation, we mean that there's some sort of relationship between two things, right? And in this case, two variables. So to talk about the correlation, we first need to talk about response and explanatory variables again. So we talked about the response and the explanatory variables before in chapter 1, and all we said back then really was that, okay, if this is your x and this is your y-axis, then the response variable has to go on the y-axis and the explanatory variable goes on the x-axis, right? So that's why I prefer to use the terms response and explanatory variables, because it tells me which axes to put the or axis to put the explanatory variable on. But I mentioned it before, right? The response variables can also be called the dependent variable, and the explanatory variable could be called the independent variable. I'm going to stick to, or try to stick to, response and explanatory, but it helps if you're reading studies or reading other textbooks. They might use this terminology, and then you could just float between the two. So the response variable, which goes on the y-axis, it measures an outcome of a study. So it's always going to be the variable of interest. Okay. The variable of interest right? So the thing that we're studying is going to be the response variable. The explanatory variable, we said, and this is from chapter 1, right? That's a long time ago now, but so that's why we're doing just a quick refresher. But if you want more on it, although there's not much more to say, but if you want more on it, you'll have to go back to chapter 1. Oh, burn. No, it's okay. It was a long time ago. So an explanatory variable explains or influences changes in a response variable, right? And so being able to identify the response variable and the explanatory variable is going to be important, especially if we're going to be trying to graph them. It's important to put the right variable on the right axis, of course. So just as a quick example, what if there was a study that collected data on age and glucose levels? Okay, so I'm not giving you any more information than that, but from there, we are able to figure out which one should be the response variable, right? Or which one would be the response variable, right? And then which one, of course, would be the explanatory variable. The response variable has to be the glucose levels, right? If you think about it this way, the response variable might change depending on the explanatory variable, right? And so the age is not going to change depending on the glucose level, whereas the glucose level might change depending on the age, right? And so that's why they use the term dependent variable, because it's dependent on the independent variable. So here, the response, the glucose level would be the response variable. Oops. Since the age of a person would not change depending on their glucose level, but the glucose level might change depending on age. But the glucose level, really wishing I had abbreviated that somehow. The glucose level might change depending on the age of the person. Okay. And so here, so depending, and that's where we get this dependent variables. Just crossed everything out there. No, it's okay. Hopefully you can still read it. And so of course, then the explanatory variable would have to be the age. Once you've decided which is the response variable, you might have more than two variables, but there's only one response variable for each study, and then everything else would be an explanatory variable. So the explanatory would be the age. Okay. Good. All right, let me bring some more up here. Okay, there's one more thing I wanted to add in here. So, okay, so we've got the response variable and we've got the explanatory variable. And so how we are going to visualize the relationship between two numerical variables is using a scatter plot. And I'm pretty sure I've made a scatter plot, maybe in chapter 1, even without introducing it. So we might have seen it, or you might have seen it somewhere else. But it's really just data points, right? But now these are pairs, X, Y coordinates, and that's what makes this scatter plot here. And so oops, that's not a curly bracket. My left-hand curly brackets always look reasonable. My right-hand curly brackets, not so much. Okay, but we visualize the relationship between two numerical variables. I will say that as long as the response is numerical, it's still true. We're going to focus on two numerical variables, but no, let's just, sorry, I'm getting ahead of myself, but we're just going to focus on two numerical variables, so that's what I will say. We visualize the relationship between two numerical variables using a scatter plot. Okay, now I'm going to bring those notes up. Okay, so like I said, the most common graphical display of how two numerical variables are related is the scatter plot. And just like we did with histograms, there are going to be three key things that we have to look at and consider when we see a scatter plot. And so the first thing is very similar to the shape. We have to look at the form, or if you want to call it the shape, that's totally fine too. And so what we're looking for is patterns and visible outliers. And we want to see a straight line, which is called a linear relationship, right? A straight line is linear. And we're going to categorize as either linear or non-linear, right? And for that, I have this cute little funny down here where, so something like this, of course, does not look like a straight line. So already, without knowing anything else, we can see that this is a non-linear pattern. And so it's a non-linear pattern with outliers. So these would be the outliers, eyes. But for some reason, I'm very happy with the data. Cute. So anyways, so that's what we mean with, we're going to categorize it as either linear or non-linear. Now, these non-linears, there are lots of different ways that we could have non-linear patterns, but because in this course, we're only dealing with linear relationships, that's how I'm going to classify them, either linear or non-linear. Okay. Next thing we're going to look at and consider is the strength of the relationship. Okay. A strong relationship is when we can really see the exact pattern and they all seem to follow some pattern and it's very, very obvious, right? Whereas a weak pattern, maybe the pattern isn't as obvious, right? And so here, for a strong relationship, the pattern is obvious. Okay. Whereas, like if if we have a weak relationship, then you might have a hard time seeing any sort of pattern, right? Could you fit a straight line to it? Could you fit a curve to it, right? Maybe it doesn't matter because you've just got a cloud of data. That would be a weak relationship. And then the last thing we're going to look at is the direction of the relationship. I'm just now realizing I should have left myself a little bit of space here. So I might have to take a little bit of time out and make that happen. But the direction of the relationship, there are only two options again. So here I want to highlight your choices. for strong versus weak. And then, so a positive relationship is one where the two variables are increasing together, right? And so as X increases, Y increases. So you get this upward trend. A negative relationship is as X is increasing, Y is decreasing. So you've got this kind of downward slope. And I want to just illustrate that, but I need to make a little, maybe I'll put a little space here. So I'll highlight this. We have to touch on each of these three things in order to fully describe the relationship, just like we had to talk about the shape, the center, and the spread to fully describe a distribution. When we're given a scatter plot, we first identify the response and the explanatory variable, then we can describe the relationship between the two variables. And so just give me a minute here. All right, so to illustrate, because I should have made these graphs and had them in the notes, but note to self. So just to show you what we're looking for. So here is, of course, a linear relationship. It looks like it would follow a straight line. Now, this line is just the general shape of the data, right? And then versus a nonlinear relationship is, especially if you have like exponential growth like this, or a lot of financial data looks like this. So there are tools for dealing with that, of course, but we're going to focus on linear relationships. For the strength, it can be a little bit tricky sometimes, but if there's a very, very clear pattern like this, then we would call it a strong, and in this case, a linear relationship. These are all linear because that's what we're focusing on. So this would be considered a strong linear relationship. I've also added the moderate because sometimes we don't have, everything on basically the same line, but there is a distinct pattern. So that's what I would call a moderate relationship, or moderately strong maybe. And then we have a weak relationship. Notice that when you try to draw a line here, it doesn't matter how you draw this line. It can kind of go any way, and it could be considered the line of best fit. So it'll kind of float around in this cloud, and that's what makes it a weak relationship. And then a positive relationship is anything that's kind of increasing like this. It's obviously my default graph, right, is a positive relationship, but you can have a negative relationship where as X is increasing, Y is decreasing, right? Whereas here, if X is increasing, Y is increasing as well. So let's have a look at an example. The scatter plot, and this is the scatter plot, shows the relationship between high school graduate rates in all 50 US states and DC, and the percent of of residents who live below the poverty line income. So the poverty line is defined as income below $23,050 for a family of 4 in 2012. And we are asked to describe the relationship between the percentage in poverty and the percentage of high school grads. So first things first, our response variable is the percentage in poverty. Why? Well, because it's on the y-axis, right? And so let's just jot that down here. So this would be our response variable, which makes the percentage of high school grads the explanatory variable. In this case, I have to think about it before I say it, put my foot in it, but it's not obvious to me which one should be the response and which one should be the explanatory variable. So the percentage in poverty depends on the percentage of high school grads is what we're saying here, but maybe the percentage of high school grads depends on the percentage in poverty. And that can happen, and that's okay. But usually in those cases, you'll be given the graph like this, and then we know that the percentage in poverty is the response variable, and the percentage of high school grads is the explanatory variable. So then if we had to describe this, right, the relationship between percentage in poverty and the percentage in high school grads is a moderately strong. So I did throw in that moderately, right, just because we've got kind of bounds like these. We can see that there's a trend here and there is a pattern, and it looks linear and it looks negative. It's not, crazy strong, but it's not weak either. We can see it. So that's why I'm going for moderately strong. And maybe I should remove these because it kind of looks weird. Okay. So it's a moderately strong negative linear relationship. Notice that you have to touch on all three. We need to talk about all three. To describe the relationship. Yeah. Good. All right. Oh yeah, I forgot I had this. So instead of a scatter plot, we could make a catter plot. Instead of a scatter plot, we could make a catter plot. This is a catter plot. It's a joke, obviously. The dots are replaced with cats, and yeah, you give a bunch of statisticians, mathematicians free reign of whatever packages they want to build. Yeah, they're going to make a catter plot replacing the dots in a scatter plot with cats. Here are some cats, here are other cats. Together they make a bunch of cats. And I had to include this because I have no idea what it's a nonlinear relationship, obviously, but also really kind of fun that you can make that in R. And I have the R code in the notes. I'm not going to bring that in here because we're not going to talk about it. And although these look, I haven't tried them recently, but they look pretty basic, so they should still run and they shouldn't be deprecated or anything. And this is just, you can ignore that. I couldn't figure out how to make it not show up. So anyways, so that's a catter plot, just kind of cute. Let's talk about why we want to have a linear relationship first. So we want our relationship to be linear because it opens up a lot of calculations and analyses that we can do. So for example, we can fit a straight line to the data points, and that's what we call a regression. We can measure the strength and the direction of the relationship, and that's the correlation. And I guess I combined those two. We can measure the variability, which is going to be with R squared. We haven't introduced any of these yet, but it's good to kind of see where we're headed. And of course, we can predict future values using a linear model. And so this is kind of why we're here. This is the main, maybe I'll go here. The main use for regression, right, is to predict future values. Okay. Not necessarily later in time, but kind of along the same lines, what do we predict would happen, right? And no, that doesn't look like, looks weird. Anyways, so that's where we're headed. That's what we want to be doing. So I have mentioned, I touched on it and then I got out of Dodge. What happens if we have nonlinear data? Okay, so we said, okay, we're not going to actually look at nonlinear relationships, but we need to know what to do or kind of where to go next if we do find we have nonlinear relationships. So before we move too far away from talking about the shape, so linear versus nonlinear, if the relationship is not linear, you could look closer at each of your variables, right? You can make a histogram of your variables individually, and if one or both of them are skewed instead of normal, right, we're going to see a nonlinear relationship in the scatter plot, right? And so we need both our variables to have a normal distribution individually in order to get that that linear relationship. If you're finding that one or two of the variables are not normal, right? So non-normal, they might be skewed, they might be bimodal. You could try applying a transformation to the data. And I want to add a page here. There are lots of different transformations. A common transformation that we do is a log transformation. So we take the log of the values of each of the values. So a log transformation is common, especially if we are dealing with money. Or a lot in chemistry, they like to do log transformations. So a log transformation is common, but there are other ones too. I gotta grab the rest of this list here. Hey, I had it here. I should have just grabbed the whole list. So one of the most important transformations is the log transformation. We use the natural log, so ln instead of log. Log base 10 is log, and ln is the natural logarithm. And so here ln is the natural log versus instead of log base 10, which is the common log, I think it's called. Now I'm drawing a blank. Which is just log. Okay. We're not going to do any transformations, but we need to know that that's something that we could do. So if we've performed a transformation, you need to take it into account when you interpret your results. So when you do your line of best fit, if we're predicting values, you have to remember that you might be predicting the log of that value. And so you'd have to unlog it, right? Unlog it. Yeah, let's leave it at that. Take the exponent. Anyways, so you have to undo the log, or you have to undo your transformation in general before you can interpret your results, right? And so that can make it kind of tricky, but it is a good tool. And so often what happens is once you've taken a transformation, then the nonlinear relationship turns into a linear relationship, and then you can model it using the tools that we're about to learn, right? So often a transformation will turn a nonlinear relationship into a linear relationship, and then we will be able to apply the analyses we will cover in this chapter. We haven't covered it yet. We will cover in this chapter. Okay. So that's why we focus on linear relationships, because we're going to try to, even if we end up with a nonlinear relationship, we end up just trying to force it to become a linear relationship anyways. So as long as we're able to deal with that, then it's kind of a natural next step if you go on in statistics. Okay, let me clean these up here. Okay, so just like when we think back to when we were describing the distribution of a histogram, right? We decided that, okay, well, when we're just describing it, then we'll just eyeball it, right? Where's the center? What's the spread? But then we developed numerical measures for the center, which is the mean or the median, depending on the shape, right? And then the spread, which was either going to be the standard deviation or the interquartile range, again, depending on the shape. So in a very similar way, the correlation between two variables provides a numerical measure of the direction and strength of a linear relationship. So a couple of highlights I want to make here. It has to be a linear relationship. And here I'll highlight the definition of the correlation. Well, I guess it's not a definition really, but that's what it does and what it is. Maybe it is the definition, not formally, maybe. Okay, so the correlation between two variables provides a numerical measure of the direction, right? So either positive or negative, and the strength, whether it's strong or weak. Okay. So here, right, the direction, which was positive or negative, and the strength, which was strong or weak. So depending on what textbook you're reading on, correlation is denoted by a lowercase r. Sometimes a capital R is used. I'm so used to just using a lowercase r that I'm going to stick with that. But if you see a capital R, they are interchangeable. Okay, so of course, R is the programming language that you might be using, so don't confuse it, but context will tell you which one it means, right? So, so correlation, we're going to denote by a lowercase r. And so correlation has some key properties that we need to remember and kind of be able to work with. So R can take on any values between -1 and +1. And the strength of the linear relationship increases as R moves away from 0 towards either -1 or +1. And we're going to call correlations between -0.5 to 5 weak. And then anything beyond 0.5 up to 1 on either end we'll call strong in general. Those are just kind of rough guidelines, but sometimes it's nice to have kind of a cutoff point. And then the direction of the linear relationship is simply reflected in whether it's positive or negative, right? So that's nice. Right, so what we end up with is basically this kind of number line, right? So R is on this number line, and it can be between -1 and +1, and of course centered on 0. So what we said was that, okay, anything between -0.5 and +0.5 we'll consider weak, right? So not very strong, and that's just how it is. Okay. Whereas, and notice I'm using round brackets. That's because it's just a rough guideline. Okay, so here from roughly positive 0.5 to 1, well, definitely 1. It would be strong. And same thing from roughly negative 0.5 up to negative, or I guess down to negative 1, it would still be strong. And then from 0 to positive 1, here we have a positive relationship. And of course, between negative 1 and 0, we have a negative relationship. Right? So the correlation, these facts, right, we can summarize with this graphic. So that's all I'm doing here, is I'm just kind of showing you what all these things are saying, right? But if you don't like the graphic and you want to stick to straight facts, then that's okay. All right, good. Let me add a page and bring this example up. So just kind of getting familiar with the correlation and some of those correlation facts. Oops, where's it? Here. So it's the same graph that we were looking at before. I think I rely on that data set pretty heavily here, just to illustrate all these concepts. So I'll use the scatter plot, which is this one here, to determine which of the following is the best guess for the correlation between the percentage in poverty and the percentage in high school grads. So I encourage you to give it a pause, give it a try. So one of these is the correct one, and see where you get to. Okay, I'm back. So first things first, we can see, mostly because we have the line of best fit already on here, so that's kind of helping us, right? But we can see that we have a negative relationship, right? And so here we can see that we have a negative relationship. Oops. Which means that it can't be any positive values, right? So those are eliminated right away. Then I'm going to look at the remaining numbers here. So I've got negative 0.75, negative 0.1, and negative 1.5. But we know that the correlation can only be between negative 1 and 1, right? So we can't have a correlation of negative 1.5. And so this one, right, we can't have a correlation beyond plus minus 1. Okay. So, okay. So that's good. So now we're really only choosing between two here, two options. And negative 0.1 would be just a cloud of data, because that's really, really close to 0. Right. And so, but we can see an approximate pattern here, right? We can kind of corral most of them in between here. Let's see if I can kind of, so moderately strong, right? And so for that reason, I'm going to pick this one, right? This one would look like a cloud of random dots. Okay, just to give you an idea of negative 0.1, what it would maybe look like. Okay. So good. I've got another example down here, I'm pretty sure. Yeah. Which of the following has the strongest correlation? All right. So we know the correlation um, of -1 and +1. Those are our strongest correlations. So if we have a correlation of 1, it means your dots are always on the exact same line and there's no variability, right? And so if we look at these, the first plot is a decoy. Why? It's a super strong relationship, but it's not linear, right? And so it's not going to have a very strong correlation. The reason for that is, so I want to show you, is because if we fit a line of best fit here, these dots all of a sudden are not close to this line, right? And so the correlation is really a measurement of how close to the line things are. It's a little bit more than that, but it's nice to think of it that way. And so when we see this, a lot of these points are kind of far away from the line unless you're crossing over here and here, it's a really bad fit, right? And so uh, it would be low for this one. And then as we move across, right? So low correlation, right? Because it's nonlinear. Also, the correlation, we can calculate it for any data, but we should only use it for linear data, right? So that's up to us as the kind of operator. We need to make sure that we're not calculating correlations when they're not appropriate, right? So between these three, right, it looks like B is the strongest. And then I would put D next because there's still a clear pattern here. And then C, although we could maybe see some sort of pattern, it's pretty weak, right? And so so B is the one that we would want. Okay, good. Can't remember what we do next. Oh yeah. So when I took my first stats course, it was Stat 230. And my prof at the time, later on he became my master's supervisor. So but he was really scary in that first course. And he just stood at the front of the class and he just yelled, "Correlation does not imply causation." And now I guess I'm doing the same thing, but hopefully not as scary as it was then. So it's really, really important that we're not throwing the word causation around, or you don't want to say because two things are correlated, even if you have this really strong correlation here, you're not allowed to say because correlation does not imply causation, right? And so you can't say that a change in the explanatory variable causes a change in the response variable unless you've done a very strict experiment, right? And which you probably haven't. So just because two things are correlated, so you can say that they're associated, right? Or there is a relationship, does not mean that one variable causes changes in the other. So it's reasonable to assume that ice cream sales are positively correlated with the temperatures outside. However, we can't argue that as long as we sell lots of ice cream, the temperatures will stay high. That's not really how it works, right? And there are lots of other examples. And I've actually, there have been times where, I'm driving and I'm listening to the radio and they're claiming causation just because there's some correlation. And makes me want to call in, and correlation does not imply causation. So you have to be really, really careful, right? You are allowed to say that because two things are correlated, there's an association there, right? There is some relationship there, right? But they're not, there's no causation necessarily. And then kind of my favorite follow-up to that, because it's just perfect. I used to think that correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. Right? All right. So let me just organize here. Wow. Okay. So before we go through this nasty formula for the correlation, well, it's not going to be that bad. We're going to work through it, but and we are going to calculate it by hand, but that's mostly just me being weird and old school. We would use software to do this, right? But it is a really good skill to be able to look at something kind of scary looking like this and be able to pick it apart and to be able to understand what needs to be done here. Okay, so first thing we've got here is, of course, R, which is the correlation, which we are trying to calculate. Then we have summation notation, which we remember from when we calculated the standard deviation. So we've seen some of these summations before, right? And so if we have the sum of x, y, what we need to do here, this is kind of a new one, is we need to take our x column and our y column, and we need to multiply them together and then add them up. Right, and so here, this is kind of the new one. And maybe what I'll do is I'll kind of bump this all down and give myself more space for now. The sum of x times y is we need to multiply each x and y, maybe I should say each row of x and y, each row of x and y in a new column, and then add them up. Okay. N is, of course, just the sample size, right? And so the sample size is the number of points. So how many XY coordinates do you have? And anything that's kind of that we know already, I'll just do in light blue here. N is the number of XY coordinates / points. X bar is the mean of x, which we definitely know how to calculate, and y bar is the mean of y. So if you have an x column and a y column, and I ask you to find the means of those, you can do that, and those are the values that you would use here. The sum of the x's squared, well, that is something we've done before, right, for the standard deviation, but I'll put it down here. The sum of the x's squared is make a new column of each x squared, then add them up. Okay. N is, of course, the sample size again. X bar is just X bar. And just as a side note here, it's just X bar, then squared, and then multiplied by N, right? So you take your X bar, you square it, and then multiply by N, and then subtract it from the sum of the X's squared, and then take the square root. Oh man, yikes. Same thing over here, you do the same thing but with the y's, right? And so over here as well, just as a note, it's just y bar squared. And this summation here helps if I don't cross out something. The sum of the y's squared is the same as the sum of the x's squared. We're just going to make a new column of each y squared, then add them up. Okay. If we're lucky, we don't have to do that. Okay. So if we're lucky, then if we have the covariance, it's called, and we denote it by S subscript XY, it's the standard deviation of XY, kind of a combo, if you want to think of it that way. It's called the covariance, right? But that's where the notation came from, SXY. And so if you have the covariance, right, and I tell you the covariance is this, then it's way easier to find the correlation, right? Because then this is the covariance and SX is the standard deviation of X. And of course, SY is the standard deviation of Y. Oops. Helps if I finish what I was writing. I'm scared to look back at these notes and realize how many times I've skipped words. I tend to do that if I'm kind of thinking ahead too much. No, just thinking too much. Too little, maybe. Okay, so then you would need the standard deviation of X and the standard deviation of Y, which you know how to calculate, but that's actually, all these calculations are actually built in to this formula. So I wouldn't, if you don't have any of those components, I would just go ahead and use this one formula instead of trying to do them all individually, but you can. So if you need to calculate the covariance, right, then there are two options in terms of formulas that you could use. So sometimes it'll be given to you, that's the easiest scenario, and then sometimes you'll have to calculate it. You could use the first option. I actually prefer the second option. I prefer this option, okay, which I realize now I've got a couple of some subscripts on here, the xi, you can just ignore that I, it's just for the ith observation, but you can just ignore it. So this option says that the covariance, we can find it by taking the sum of xy, which is also what we used for the correlation, right? But this is only part of that calculation, minus n times x bar y bar divided by n minus 1, right? So a little bit easier because you only need the sum of the x y's and then of course x bar y bar. So I prefer this option. Then you would only need to make a new column of x times y and then add those up. And then you have the covariance. Okay. I wanted to show you what it looks like on your formula sheet. I give you all of these. Right, so covariance and correlation. On this formula sheet, I have the one that I prefer up top, right? And so this is only if you have to calculate the covariance. Or the correlation, if you need to calculate the correlation, you have two options. Definitely, if you have each of these three components, the covariance, the standard deviation of X, and the standard deviation of Y, then I would definitely recommend that you use this one. Right? And I've even got a note that lowercase r and capital R are used interchangeably. Okay? But I'm going to use lowercase r in these notes. I can't bring myself to use an uppercase R for correlation. Okay, so let's consider an actual calculation. Ooh, scary. I know. It's actually where I got the idea to make you practice the response in the explanatory variable. So we're going to calculate the correlation between age and glucose level of the 6 subjects below. So we decided that age was the X variable and the glucose level was the Y variable, right? Notice that each subject has an X coordinate and a Y coordinate, right? And that's what makes a point on the graph. So what do we need to do? If we have to calculate the correlation, right, then let me grab the formula that we're about to use here. Without any other knowledge, we're better off using the big formula because otherwise I would have to calculate the covariance and then calculate the standard deviation and then calculate this of X and then calculate the standard deviation of Y. And that's just a lot of different components. I'd rather just do one big nasty formula instead. I wonder if I did. Okay. So I'll keep this here so we can reference it. Because, oh, and what I want to do too is maybe just copy, crop. I want to just bump this table, give myself as much room as I can. And sorry, I should have done this kind of offline here, but too late now, I've committed. Okay. So what we're going to do, right, is there are a couple of different sums that we need, right? And so what I'm going to do down here is the sum is going to go down here. So the sum of X, the sum of Y, and then I need the sum of X times Y. So what I'm going to do is I'm going to make a new column of X times Y. I also need a column of X's squared, right? Because I need the sum of X to find X bar. I need the sum of Y to find Y bar. That's fine. But then I need my X's squared. So, and I'll clean up this table in a little bit here, but I'll make an X squared column. And finally, I need a Y squared column. And then I'm going to find all the sums down below here, right? And so I'm going to fill in this table, but I encourage you to try it on your own to see if we get the same thing. Meet you back here. Okay, so time to check in. Where did this come from? Okay, so we did all our numbers. Truth be told, I did just copy these from somewhere else. So hopefully they're right. I did not bother checking them, but hopefully they're good. So I'll get confused messages if they're wrong, but they should be okay. I'll check them later. Okay, so we've got our sums, right? So down here, we've got our sums, and now we can kind of plug in a lot of this information, right? So we have the sum of X, Y, right? And so if I bring this down here, so it's on the same page, right? the sum of xy is going to be replaced by 20,485. What's n? N is the number of subjects, right? Or the number of pairs that we have, right? Which is going to be 6, right? And so here I'll kind of put it out here. N is 6. Guess it helps if I show it including the last one there. Okay, so n is 6. X bar, well, we can easily find X bar. Now that we have the sum of the x's, right, X bar is going to be, oh, that's not the right color. I'm just trying to see what the best way of showing it is. So it's from here. And we know how to find these. So maybe I'll just do these. I'll fill those in later. But the ones I want to focus on are the sums of the x's squared. Different colors. Running out of colors here. Oh, here's a fun palette. The sum of the x's squared would go there, right? So it takes that whole area, and then the sum of the y's squared going here, right? And then once, so I'm going to calculate the x bars and the y bars, and then I'm going to plug them in. And then what I want you to do, because you are going to have to do this calculation by hand, so it is really important that you know how to do it. But being able to pick apart the formula, it's then it's not so bad, right? So what I want you to do is try to do this calculation on your own and then meet me back here. Yeah. Okay. So I plugged in all my values, right? Making sure that you keep those square roots and you put the squares on the right values. And then we just methodically work through, right? Following BEDMAS, where we need to multiply 6 times 41.17. Oh, I guess I did that offline too. I just rounded to 2 decimal places. That is going to affect my results. It's okay, because if it was super, super important, we would use software, right? We wouldn't be doing it by hand. And it's going to be pretty close anyway. So I rounded to 2 decimal places, 41.17 for X bar, and Y bar turned out to be a nice 81. So that's good. And so I plugged in those values, and then so you multiply in the numerator 6 times 41.17 times 81, and you get 20,008.62. I almost said pennies, but it's not money. That's okay. And then it kind of simplifies slowly in the square roots. So in each of the square roots, deal with that x bar squared and the y bar squared first. So solve those, and then multiply by 6, and then subtract it from the sum of the x's squared and the sum of the y's squared. Okay, and then once you have those values, then take the square roots and then multiply them together, and then divide by divide into the numerator, and you should get something like 0.5283640326, which I have rounded to 4 decimal places, 0.5284. You don't want to go to too few decimal places, so 4 seemed like a good stopping point here. Of course, it would ask you or tell you how many you need. So here it didn't say, so I just went a little for 4. So knowing the components and how we put them into the formula, now you can tackle finding the covariance as well, right? Because the covariance is just the exact same formula that you had in the numerator, except none of that nasty square root stuff in the denominator. You just have divided by n minus 1. So finding the covariance is a lot easier, right, than finding the correlation. So now that we've seen the correlation, you can handle this calculation as well. We're not going to do it together though, but I will make you do it later. But we're not going to do it together. Oh, rude. I know. Okay, so good. So this looks like a not very strong relationship. There's probably something going on there, but there are definitely other factors that are coming into play for the glucose level, not just the age, right? So that's what that's telling us. Okay. So the last thing that I want to talk about is I went a little off-roading here in my mind, I guess, because the textbook introduces the residuals after we fit the line. But I think here I just kind of wanted to introduce them and get them out of the way. We don't need to have the line yet in order to talk about the residuals. I think it's the last thing. Oh, good. Yeah, so the last thing I wanted to talk about, and maybe I'll just got the space, got the real estate, why not? Let loose here. Okay. So we've talked about, okay, so we will find the line of best fit. So there will be some straight line, okay? And from that line, all the distances from each of the points, which we'll call our actual values, to the line, those are the residuals. So the line of best fit, it doesn't go through all the data points, right? And that's okay. So the distance between our actual data points and the line that best fits our data will be our error or residual. I prefer to call it residual just because I have a hard time saying error. I don't know. It's so hard for me. Error. So I call it a residual. But it is the error term, right? And so it's how, if you want to think of it as how wrong your line is, right? That's okay. Residual sounds nicer. So the residual is going to be the difference between the observed y, which is the actual y value that we saw in our data. For example, in this data set here, these would be our actual y values, right? So those would be our actual y's for each of these x's, right? And then we're going to be able to find predicted y's. Now, they're called y hat, and I'm realizing now my mistake by pulling it up, but that's okay. The predicted value of y is just going to have a hat on it. So for now, just ignore the y hat because we haven't introduced it. But the line of best fit represents the predicted values at each value of x, right? And so here, these are the actual y's minus the predicted y's. And the residual is denoted by a lowercase e, because R is, of course, the correlation. So we run into kind of some notation issues. Oh, that was taken. Okay, so let's use E for error. Sounds good. So kind of a fun thing, and it's because of how we build the line, but it's still true and it's still cool. The sum of the residuals will always be 0. So if you add up your residuals, you will get to 0. So let's have a look at some of these residuals here. How do they behave? Helps if we zoom in a little bit, I guess. So this is our line of best fit on here. And so these would be the predicted values of y, right? The predicted value of y when x is 90 is roughly, I don't know, somewhere between 8 and 10. Kind of lost my line there, but whereas if we look here, there was no actual data point. Well, maybe here, 90, right? And so if we kind of, maybe that was, right? This would be our actual, so the predicted y is roughly 9, let's say, but the actual y at x equals 90 is roughly 14. Right? So our actual value is 14, whereas we were predicting, and here it kind of roughly, but we're talking about the same value of x, right? So there we're predicting, we go to the line and we predicted it would be 9, but what we actually saw was 14, right? When x was 90-ish. Right? And so we can calculate residuals for all of the points, right, individually. And so here we have DC. We find that the residual is 5.44. It's a distance of 5.44 between the actual and the predicted. And notice, because the residual is the actual minus the predicted, if the actual is higher than the predicted, then you get a positive residual. Whereas if the actual is less than, so if we're looking at, RI is Rhode Island, I think, right? The states, who knows? Rhode Island, they say the same thing about us, I'm sure of it. So Rhode Island had an actual value close to 10 when x was 82, 81-ish, right? But the predicted value was somewhere around 15, right? And so we find, or we're given, that the residual is 4.16, but it would be negative, right? Because the actual minus the predicted would be negative. Right, so that means it's less than predicted. So we can talk about over predicting, under predicting, right? And so we're going to get some positive residuals, and they're all the ones above the line here. And then we're going to get some negative residuals, and they're all the ones below the line. So if we add all those up, that's how we get the fact that when we add them up, the sum will always be 0, right? And so points above the line are over predictions, right, which yield positive residuals, while points below the line are under predictions. Wait, am I doing that right? No, it's the opposite. I over predicted if it's below the line, but it's less than predicted. That's what threw me off. Excuses. Here, all I need to do is change one thing. Points below the line are over predictions because the points are below the line, right? Meaning we would have negative residuals. Sorry, oops. I was doing the Now I need to really think about this. This was an over prediction. The point is below the line, and actual minus predicted. My actual is 10, let's say, and my predicted is 14. 10 minus 14 is a negative number, right? So you can always kind of talk your way through it. Yes, I had to do it myself, and that is totally fine. I've been clear about my corrections here. So then I'm just going to cheat here. So while points above the line are under predictions, which mean we have positive residuals. Okay. Good. But overall, right, we're going to have some positives and some negatives. And if we add them all up, they're going to add to 0. And that is because of how we construct our line, which we will be doing in the next part. So I will see you then.